In this element, we're going to talk about axial symmetry. What is axial symmetry? Well, it is just a mirror reflection, a reflection across a line. This line we call the axis. For example, this star is symmetric with respect to this axis, the red line, because this point and this point are mirror images if we assume that this red line is actually a mirror. And this point and this point are also mirror images. Here, let me explain what I mean. I call 2 points mirror images with respect to this mirror if the line defined by the 2 points is perpendicular to the mirror and if the distance from each point to the mirror is the same as the distance from the other point to the mirror. So essentially, this point is the midpoint of this segment. And if a point lies on the mirror, then we say that it is its own reflection. So, in the example with the star, this point is its own reflection because it lies on the mirror, and this point is its own reflection because it lies on the mirror. Similarly, we can take any point inside of the star and find its mirror image. The star is symmetric with respect to this axis because if we map each point onto its mirror image, then we're going to get exactly the same picture. Since each point in the star has a mirror image inside of the star, and each point outside of the star, for example here, has its mirror image also outside of the star. And now let's ask ourselves, what's the reflection of this line with respect to this mirror? In other words, what's the symmetric image of this line under axial symmetry with respect to this axis? Well, first of all, notice that this intersection point is its own mirror image, and therefore the mirror line would also pass through this point. Now let's take a random point from the blue line and find its reflection with respect to this line. It would be this point, such that this length equals this length, and such that this line is perpendicular to this line. Then this point would map to this point, and vice versa. So we got that the mirror reflection of this line would pass through this point, and it would pass through the image of this point, which is this point. And so we can draw a line passing through this point and this point, which is this line, and it turns out that this line is exactly the mirror image of this line. This means that if we take any point from one of the lines and find its symmetric point, then it would lie on the other line, the image of the first line. So if we take this point from this line and find its mirror image here, then this point would lie on this line. We should mention that if we take a line that is parallel to the axis of symmetry, then its reflection would also be parallel to the axis of symmetry. So we would have a right angle here, here, but also here and here. And we would have this length equals this length. And if we take another point and reflect it, we're going to have this length equals this length and right angles here. Essentially, we get two rectangles, one here and one here. And what if the blue line coincides with the red line? Well, then all the points would be stationary. They would be its own image. And so the image of the red line under symmetry with respect to itself is just the red line itself. Now take a look at this picture again. See that under reflection, this line stays at its place and this line goes to this line. And therefore, this angle, which is defined by this line and this line, goes to the angle between the reflections of the two lines. So the reflection of this line is here and the reflection of this line is here. And so this angle goes here. And because reflection preserves angles, this angle equals this angle. This property is what makes you look like yourself when you look at a mirror. Now, of course, we have that this angle equals this angle and this angle as well. And from the sum of the angles in the right angle triangles on the picture, we get that all the angles here, 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 and here equal 90 degrees minus this angle. We know that this point maps here, and this point maps to itself, and therefore this segment maps to this segment. And so the two segments must be equal. Let's call the length of this segment and this segment y. For the same reason, because this point goes here and this point stays constant, then this length equals this length, and let's call it x. And therefore, this length, which is the difference between x and y, and this length, which is again the difference between x and y, are equal. This equals x minus y. What you see here is called an isosceles triangle. An isosceles triangle means that two of its sides are equal. If two of its sides are equal, it means that this part of the triangle is symmetric to this part of the triangle with respect to this axis. Now suppose that you have a triangle for which this side equals this side, then you can always construct the angle bisector of this angle such that this angle equals this angle. We know that this line stays at its place under symmetry with respect to itself. We also know that this angle equals this angle, and therefore the reflection of this angle is this angle. And so this line must be the reflection of this line with respect to this axis. And now, because this length equals this length, and these two lines are reflections of one another with respect to this line, then it follows that this point must be the reflection of this point with respect to the same symmetry. And from here, this configuration inherits all the properties that we found for symmetric points. So this angle equals this angle, this is a 90 degrees, this length equals this length, and so for an isosceles triangle, all these properties hold, meaning that the angle bisector, the altitude in the triangle, which is the line that makes a 90-degree angle with the base, and the median, which is the line connecting the vertex of the triangle with the midpoint of the opposing side, these are all the same line. Here's another situation in which you may suspect that you have an isosceles triangle. The situation is, you have a triangle for which this angle equals this angle. Then what do? Well, we can again draw the angle bisector of this angle right here, and then we get that this angle equals this angle, and this angle equals this angle. And now from the sum of the angles of this triangle and this triangle, we find that this angle equals 180 minus this angle, which equals 180 minus this angle, which equals this angle. And so this angle equals this angle. But the sum of the two angles is 180 degrees. And therefore, this angle must be a right angle, and this angle must be a right angle. We know that this angle equals this angle, and therefore we can conclude that this line is the reflection of this line under symmetry with respect to this angle bisector, and vice versa. But now, how do we show that this point is the reflection of this point? Well, if we take the reflection of this point, we know that the line it's going to create, the line between this point and its reflection, is going to be perpendicular to the axis of symmetry. But we already have a right angle here, and therefore this point must be the reflection of this point. And so we inherit the rest of the properties, that this length equals this length, and that this length equals this length. If we have a triangle in which the angle bisector is the altitude, from the sum of the angles in this triangle and this triangle, it follows that this angle equals 90 minus this angle, and therefore the triangle is isosceles. If in a triangle we know that the altitude is the median, then it immediately follows that this point and this point are reflections with respect to this line, and therefore this triangle must be isosceles. Now, let's look at the following situation. Suppose that in a triangle, the angle bisector and the median coincide. It turns out that such triangles are always isosceles. Let's assume that there exists a non-isosceles triangle that satisfies these conditions. First of all, we know that this angle equals this angle, and hence this line and this line are reflections of one another under symmetry with respect to this angle bisector. Now let's draw this line, which is perpendicular to this line and passes through this point. Then this point and this point must be reflections of one another with respect to the symmetry, because in this triangle we have that the altitude coincides with the angle bisector, and so this here is an isosceles triangle. Now let this point be the reflection of this point with respect to this line. Then we know that this length equals this length, and we know that this angle equals this angle. And now, since this angle is 90 degrees, and this angle is 90 degrees, and this angle equals this angle, we get that this angle equals 90 degrees minus this angle. And since this is a straight line and this is a straight line, we get that this angle equals this angle. And so this here is an isosceles triangle because this equals this from the median and this equals this from the symmetry. And so in this isosceles triangle, this is an angle bisector, so it must also be an altitude. And now take a look at this triangle. It has angles 90 degrees, and some other angle. So the sum of the angles of this triangle cannot be 180 degrees. It is actually larger. This is a contradiction. The contradiction confirms that any triangle in which the angle bisector and the median coincide is an isosceles triangle. You should be really careful when applying symmetry, because sometimes things can be misleading. For example here, suppose that you have 2 points, this point and this point, in a line of symmetry, and you're trying to prove that the 2 points are symmetric. You found a point on the line such that this length equals this length, and you found another point on the line such that this angle equals this angle. And you might be tempted to say, therefore, this point and this point are symmetric with respect to this line, but see, it's not actually the case. It's obvious from the picture that they are not symmetric. In fact, Here is the location of the actual symmetric point of this one. For it, it is also true that this length equals this length and that this angle equals this angle, but it is actually the point that we're looking for, and this point is not. So you should be careful when making conclusions when using symmetry. A nice property of circles is that any circle is symmetric with respect to any of its diameters. Suppose that we have a circle and we draw this diameter. Then, if we take a random point on the circle, its symmetric point with respect to that diameter would also lie on the circle. You can easily see this by considering that the distances from each point to the center of the circle are equal. Suppose that I take this point and I drop the perpendicular line to this line from this point, and I intersect it with the circle here. Then I know that this equals this, and so this triangle is isosceles, and this is its altitude, and the altitude is a median in the isosceles triangle, and therefore this length equals this length, meaning that this point and this point are reflections of one another with respect to this line. Suppose we have a segment. The line that passes through the midpoint of that segment and that is perpendicular to the segment is called the perpendicular bisector of the segment. You can now easily see from the symmetry that any point that we chose on the perpendicular bisector of a segment is such that the distances from this point to the two endpoints of the segment are equal. Or in other words, this triangle is isosceles. Here's the optional problem. We have a line, and we have 2 points on each side of the line, and we know that there exist 2 points on the line with the following properties. This length equals this length, and this length equals this length. We need to prove that this line is perpendicular to this line. And here's the solution. We know that this equals this, and therefore this triangle is isosceles. Similarly, because this equals this, we know that this triangle is isosceles. Now let's take the midpoint of this segment, let it be here, and let's connect it with this vertex and this vertex. We know that a median in an isosceles triangle is also an altitude, so this angle here is 90 degrees. Similarly, in this isosceles triangle, this is a median, and so it's also an altitude. Therefore, this angle is 90 degrees. And now we have a 90 degrees here and a 90 degrees here, meaning that this angle is 180 degrees, which means that this point, and this point lie on a straight line, and hence the midpoint coincides with the intersection of this red line and this dashed line. And now it's clear that this line is the perpendicular bisector of this segment, and that this line is perpendicular to this line.